Welcome geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Today we will go into Chapter 5, Chemical Energetics for AS. We will apply Hess law to construct a simple energy cycle and carry out calculation involving such cycle. First of all, let's go into definition of Hess law. Hess law stated that the enthalpy change for reaction is constant, regardless to route taken, provided final and initial condition are the same. So this definition, we have 2 points here. So where the first part, the enthalpy change for reaction is constant, regardless to route taken. It is the first point. And the second point here, it's provided final and initial condition are the same. So if it is a 2 marks question for the definition, the first point we could get 1 mark, and the second point will give us the second mark. Let's see how we could actually explain this. So let's say A reacts with B, give us C. So we can get C from A plus B with 1-step reaction or a 2-step reactions to go. So if it is a 1-step reaction, we will have 1 delta H. So let's say it is delta H1. So we could actually get C from A plus B with a 2-step pathway. So let's say A reacts with B, we could also get E plus F. And E plus F react, they can give us C. So this pathway, we will have 2 steps reaction to get C from A plus B. If it is a 2-step reaction, then we will have 2 delta H. So we have delta H2 for the first reaction, and we have delta H3 for the second reaction. So if to get C, we can get 1-step reaction, which is a shortcut, and we could also have a long-step reaction to go. So no matter we are using a 1-step reaction or 2-step reactions to get C, the enthalpy change of the reaction is constant. So this, we could actually put them into this equation, where delta H1 is equal to delta H2 plus delta H3. Let's go into question as the example to construct a Hess law cycle, and we move into the calculation. So this question requires us to calculate the standard enthalpy change of formation for methane, which is CH4 here. And given us with the standard enthalpy change of combustion of methane, graphite, and hydrogen gas. So without any equation given, we could actually construct our own equation based on the definition that we have learned. So where enthalpy change of formation of methane is actually 1 mole of methane is formed from its element in their standard state. So the element to form methane is carbon in solid state and hydrogen gas in gaseous state. So to balance out this equation, we need 2 moles of H2 gas. So this is the enthalpy change of formation that we need to find. So for enthalpy change of combustion, for the definition to go is actually 1 mole of compound is burned completely in excess of oxygen. So therefore, methane is the reactant in the combustion. So where arrow point from methane with excess of oxygen to produce carbon dioxide gas and H2O liquid. So this reaction involves 1 mole of methane. So therefore, the enthalpy change is negative 890.2. So next to go, we have standard enthalpy change of combustion for graphite. So graphite, it's carbon. So if we burn carbon with excess of oxygen, we will get carbon dioxide as the product. And this involves 1 mole of carbon. So therefore, the enthalpy change that involved here, it's negative 393.4. So next to go, we have enthalpy change of combustion for hydrogen gas. So this value, it's for 1 mole of H2 gas involved in the combustion. So since the reaction here involves 2 moles of H2 gas, so it will give us 2 moles of H2O form. And arrow is pointing from H2 gas to H2O with excess of oxygen. So and the enthalpy change involved here is actually negative 285.7 times 2. Why times 2? It is because there is 2 moles of H2 gas involved in the reaction. So where kilojoule per mole is actually for 1 mole of H2 gas. So this is the complete Hess law cycle or energy cycle, or we could also call it as thermochemical cycle of this reaction. So with this, we could actually calculate standard enthalpy change of formation for methane. So how we could actually move into the calculation, we'll have delta HF, which is the reaction for methane. So then here, we will have a long way to reach methane with all these given equation or reactions. So you could actually see the standard enthalpy change of combustion for methane, it's not having a nice flow pointing to the product of standard enthalpy change of formation of methane. So therefore, we have to reverse the arrow to make sure the flow is pointing to our product. So with reversing of this arrow, we have to change the negative sign to a positive value. So this is how we could actually sum them up to get delta HF, where we have negative 393.4. It is for this reaction to go. And next, we have the next reaction, where it involves negative 285.7 times 2. And next to go, we got to reverse this arrow. So by reversing this arrow, we got to change the sign. So where we change it to a positive. So it plus positive 890.2. So with this calculation, we could get F. And the value that we get for this delta HF is 58 kilojoules per mole. We could actually have another type of simple Hess law cycle. So let's make this question as the second example. So where An equation is given here, and the question wants us to calculate the enthalpy change for the reaction. So normally the given question or equation, we will make it as a mainframe. And this is the enthalpy change that we need to find. So next, we could actually see the standard enthalpy change of formation of them are given. So based on the definition of standard enthalpy change of formation, it is actually the element of them. So it is 1 mole of compound is formed from its element. So therefore, we got to have the element in getting them as the reactant. For example, we have calcium sulfide. So the element to form calcium sulfide is calcium plus fluorine gas. So the arrow got to point from the element to the compound that formed. So we have calcium plus F2 pointing to calcium fluoride with the value given here, negative 1220 kilojoule per mole. So next to go is standard enthalpy change of formation for H2SO4. So to form H2SO4, we have H2, sulfur, and 2O2 as the element. So with all these elements, we could get 1 mole of H2SO4 with the value negative 814 kilojoule per mole. And next, we have hydrogen fluoride. But here, we are involving 2 moles of hydrogen fluoride. So therefore, the element to form HF, we have here, which is H2 and F2. So we will have arrow pointing from them to HF. And since it is involving 2 moles of HF here, so therefore the given value, negative 271, got to times 2. So last to go, we have standard enthalpy change of formation for calcium sulfide. So we need calcium, sulfur, and 2 oxygen gas as the element to form calcium sulfide. So arrow is pointing from the elements to calcium sulfide, and we have the value given here, negative 1434. So this is the Hess law cycle or energy cycle for this reaction. So next, we will go to move into the calculation. So delta H is the unknown that we got to find. So with all these values, we got to get a nice flow pointing to our product of the reaction. So what we could actually see here is that these 2 arrows are not having a nice flow towards the product. So we have to reverse them. So after reversing the arrow, we got to change the sign of the enthalpy change. So therefore, we will have positive 1220 for the first arrow. Then next, we will have positive 814 for the second arrow, and followed by the rest too. So where we have negative 271 times 2, and last one to go, negative 1434. So with this calculation, we could get positive 58 kilojoules per mole as the answer. After 2 examples of the questions, we could actually summarize it into 2 simple Hess law cycles, where the very first one is with standard enthalpy change of combustion are given as information. So where if standard enthalpy chain of combustion are given as information, so we have this equation as unknown, let's say. So if the standard enthalpy chain of combustion of them are given as information, so we got to point from the compound burn to the product of combustion. So we have also enthalpy chain of combustion for B with the enthalpy chain of combustion for C. So we could actually see arrows are always pointing from the compound that burn to the product of combustion if standard enthalpy change of combustion of them are given as information. So after constructing this simple cycle, when we are moving into calculation, so we have to reverse this arrow and change the sign of the enthalpy change here to make sure it has a nice flow pointing to the product of the reaction that we need to find. So the second type of simple cycle that we could have is that if standard enthalpy chain of formation are given as information. So we have this equation as the unknown, let's say. So this is what we need to find. So what if standard enthalpy change of formation of them are given as information? We could actually construct the cycle by getting the elements to form them as the reactant, and arrow is pointing from the element to the product that form. So this is the simple cycle that we could get if standard enthalpy change of formation are given as information. So for us to move into the calculation, for this, we got to reverse these two arrows in order to make the flow pointing to the product of the reaction that we need to find. So these two are the simple cycle normally they could ask. Of course, we may have other different cycles to go with different kind of questions to go.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.